Here we're going to look at two of the questions from the recent exercise on geometric sequences and series. Had some requests to go over a couple of questions because a few things are not very clear right now. So I've picked question 2 from exercise 7C and we'll look at question 5 from exercise 7D. So this is the one where there's a biologist and they're running an experiment with some bacteria, and it says that the number of new bacteria that are created are 10% more than in the previous hour. Now, very important, straight away we see that this is talking about the amount of new bacteria created every hour. So 10% more every hour are created. It says there was 72 million bacteria to begin with. And then the other very important number here is that in the first hour, the number of bacteria that were created was approximately 12 million. So the first question is asking us to find the number of bacteria that were created during the 6th hour of the experiment. Right, well, in this case, we need to think about how this number 12, the amount that was created in the first hour, is going to increase up until the 6th hour. And this here is the amount it's going to increase by 10%. So just forget the geometric formula for a second. Here's how I might actually start a question like this. So we can say that in hour 1 we've got 12 million bacteria. We'll just use the number 12 for 12 million. In hour 2 we have to apply this multiplier of 1.1 in order to get to the 2nd hour. So we do that on our calculator if we need to. Hour 3, hour 4, hour 5, hour 6. Whatever these are going to be, to get to the next one, each time we're increasing by 10%, which means each time we're multiplying by 1.1. Of course, there's a much quicker way of doing this. We could just do 12 million multiplied by 1.1, well, 1, 2, 3, 4, 5 times. That's what it's going to be. And the answer to that is roughly 19.33. So 19.33 million bacteria is how many are going to be created in the 6th hour. Common mistake might be using 72. 72 million is how many there were already, but that's not how many are being created each hour. 12 million to begin with, and then that number increases by 1.1. Now, I haven't used any nth terms or any formulas there at all, but we could use an nth term for the geometric sequence because this is a geometric sequence. It's got a common ratio each time. And that would be, in this case, looking at the formulas here, remember you get these in the booklet, so I'll just show you these now. That's the nth term formula. Nth term is the first term multiplied by the common ratio n minus 1 times. So if we want to get to the 6th term, we would use the nth term formula like this. Let's get the formula down first. So that's what it's going to be. 12 times 1.1 to the power of n minus 1. Remember, it's n minus 1 here because if we're trying to get the first term, we don't have to apply this multiplier at all. So we want n as 1, then we do n minus 1 and get 0, so then that doesn't get applied at all and we get 12. But if we want to get to the 2nd term, n would be 2, but that means that this power would reduce to 1 because you only need to do this calculation once. So to get to the 6th term, the 6th hour, we do U6, 12 times 1.1 to the power of 6 minus 1, which of course we've just done there. Okay, so that's the first question. Second question. Find the total number of bacteria that were created during the first 6 hours. Well, that is going to be all of these numbers, if we'd work them out, added together. All right, so we could do that times 1.1, do that times 1.1, and so on and so on and so on. Work out all of these, add them all up. That would be the answer. That's one way of getting it. But of course, we don't really do that because we have the sum formula here. So again, it's in the formula booklet. You've seen how this can be derived. You've got this version here, which is usually used when the common ratio is greater than 1, and this version here when it's used when it's less than 1. So we'll be using this one here. In this question then, start question B. We're doing the sum of the first 6 terms. Let's get the general nth term formula first, actually, for the sum. So we do the first term, u1, that was 12. And then it's multiplied by, in the brackets, r to the power of n. So that's going to be 1.1. Now, it is actually to the power of n. Very common mistake is people putting n minus 1 there as well. That's only for the nth term. The sum actually does have n. That's because in the nth term formula, you need to do one fewer step than the term you're on. So you want to get to the third term, it only requires 2 steps. That's why that has an n minus 1. But if you're summing them, you are going to include everything. You're not going to miss one out there. So you do actually have power of n there. Minus 1, and then that is going to be 1.1 minus 1. So that's just me. There's a point there. The camera's not very clear, but that's a decimal point there. That's just me using this formula here. In the previous video, I showed where that came from, but you don't have to really memorize that. You've just got that there. Turn it off. Okay, so if we do the value for the 6th term, so s of 6, it's basically the same thing, but now it's just going to have 6 in place of the n. So you're going to go on your GDC, you're going to type all that in, and it turns out to be about 92.59 million. So that is the sum of the first 6 terms, and that is question B answered. Question C. Find the total number of bacteria in the petri dish, I think, 10 hours later. I think this means after 10 hours in total rather than 10 hours after question B. It's not really very clear, is it? But we'll go with that interpretation. So it's actually the same kind of question. We're just now going to apply, instead of the 6th hour, it's going to be the 10th hour. So I'll just kind of squeeze this one in here actually because it's quite straightforward. Sum of 10. We're still summing the total number of these added up, this geometric series. So 1.1 to the power of 10 this time, minus 1, 1.1 minus 1 on the bottom, r minus 1. However, there's one extra part here. We have to now include the fact that there were 72 million bacteria in there already, and this sequence we're talking about is only what's been added, what's been created new. So we've also got to stick plus 72 on the end of that. So you calculate that, and you're going to get yourself around 263.25. That's going to be million. If you did interpret that as the 16th hour, which isn't unreasonable, I think it works out at about 503.4. So that's also fine as far as I'm concerned. Question D, determine after how many complete hours the number of bacteria will exceed 1 billion. Right, well, we're going to still be using the sum formula because it's the number of bacteria in total in there. But we've now got a total to aim for. So here's where an equation is going to be used. I'll just do this on here. We're trying to get a billion, which is 1,000 million. So I'm going to put 1,000 there. And the sum formula for this particular situation, as we've been using, is this. But what we're asked to find is after how many hours we're going to get the billion. That means we don't know the times. We don't know what hour we're in. Therefore, this part, the power, that's the unknown thing. So I'm going to put an x there. Minus 1 over 1.1 minus 1. Don't forget, of course, that is going to include the 72 as well. So we're solving this equation. Well, that is where the GDC comes in. So let's go on there now. And we go to the equation solver, see if you can see that. And just delete this equation that is in there already, which is the one we're going to look at in the next question, actually. If we type that in, we should be able to get the correct answer. Let's just see if that's what we get. So 1,000 equals, use the fraction button here, and it's 12 times bracket 1.1 power of x. You can see that's the unknown thing we're trying to find here. Minus 1, oh, make sure the minus 1 goes on the same line as the original 1.1. Oh, let's just got rid of it. This must be very tedious to watch. I'm not going to restart the video. You just have to watch me do this all again. 1000 equals fraction 12 times 1.1 to the power of x minus 1, close the bracket, underneath 1.1 minus 1, and then don't forget to add the 72 that was in there to begin with. So hopefully that makes sense. Then we will press solve, and it says 22.73, which means that we're going to have to go for the 23rd hour in order to get the 1 billion. So 23 would be your final answer in that particular question. Okay, so I think that's everything we need from question 2 there. I'm going to throw every single question in that exercise, but if you can do that one, you should be able to do most of them, I think. Let's have a look at something from the other exercise, 7D, is this question here with the circles. Now, there's going to be an interesting mathematical interlude here. I'm going to share with you something that I learned in maths when I was studying A-level, similar age to you, and I thought was really, really interesting and got me interested in high-level maths, actually, and this question relates to it. We'll come on to that in a second. So it starts off pretty straightforward. People are shading these circles in, and every time they get a new circle, they half the bit that's not been shaded, and they shade that in. So initially you got the whole circle free, half the circle, shading that, okay, it's half a circle. Then you take the half, you shade half of the half in, so you shade the quarter in, then you're shading half of the quarter in, so you're shading this, and it's half of that, and then so on and so on and so on. The circle has radius 4 centimeters. Okay, find the area shaded by the first student. Right, well that's pretty straightforward. We know the formula is pi r squared, so it's pi times 4 squared, but they're only shading half of it in, so it's going to be 16 times pi divided by 2. You get 8 pi, and we'll keep it in terms of pi. Find the area shaded by the second student. Right, well this person has half the circle left to use, so this is 8 pi here. They're going to shade half of that in, so it's just going to be 8 pi over 2, which is obviously 4 pi. Okay, so far so good. Find the area shaded by the first 2 students. Right, well it's going to be this one plus this one. So 8 pi plus 4 pi equals 12 pi. Not really any need to do in the nth term or some formula for this one so far. Find the area shaded by the 5th student. Okay, well, it wouldn't be that hard to carry this sequence on, actually, without bothering with the formula. So let's do that. If we look at the set of things shaded in by each student, so we're going to go for 1, 2, 3, 4, then the 5th student. So the first student shaded in 8 pi, then the second one shaded 4 pi, and he shaded 2, and she might have shaded 1, and then this last person shaded half a pi. So that's your answer there. This last student here, the 5th student, they shaded in 1/2 pi of the circle. So an increasingly small amount, it's halving each time. You can see these numbers do form a geometric sequence where the common ratio is times by 1/2 or 0.5. So you could start to make a geometric sequence here. Find the area shaded by the first 5 students. Right, well that is, again, it's pretty easy actually now that we've got this working out done. We just have to add all this together. And if you do that, pretty straightforward, it comes out as 15.5 pi. Might be worth knowing at this point how we could use the formula for this question. So if we go back maybe to question D, find the area shaded by the 5th student. Well, if we do this with the formula, we can see we need the nth term formula here. So that's going to be the starting term, which is 8 pi, times the common ratio, which in this case is 1/2, and I think I'll just use 0.5 in this case, to the power of n minus 1. So that's the nth term for this geometric sequence. If I want to find the 5th term, then I'm going to do u5, 8 pi, 0.5, 5 minus 1, so that's going to become 4. So it's going to become this, 8 pi times 0.5 to the power of 4. That's going to give me the 5th term of the sequence. And if you work that out, it will become half pi. The sum works the same way. So if we do the sum question, question E, we know the answer already, but let's do it with the formula just to prove it works. Well, the first term was 8, so it's going to be the general nth term, 8 pi times the ratio in this case. Well, in this case, actually, because r is less than 1, I'm going to use the other version. Both of these versions work fine, but it just looks a bit neater when you do this one because there's no negatives involved. This would give you a negative here, because you'd have 0.5 minus 1 here. You can have a negative, but this one just looks a bit better. And this one works a bit better when you come to the infinite sum, which we'll come on to in a second. So this one's going to be 1 minus 0.5. Remember, this one is going to be to the power of n, not n minus 1. And it's 1 minus 0.5. So if we're looking for the sum of the first 5 terms, it's going to be the same thing, but with the 5 replaced up there. And if you type in the GDC, you will get 15.5 pi, or I think it's 31 over 2 pi. Okay, so that's those. Now, the next question, question F, it says, find the number of students required to shade 99% of the circle. Well, here's where it actually would pay to use this sum formula, because we're trying to work out when the total amount shaded is equal to 99% of the circle. So we need to work out what 99% of the circle actually would be before we do anything else. The circle as a whole has an area of 16 pi, which we can get from doing pi r squared. So if we find 99% of that, if we do 0.99 times 16 pi, that is going to give us the total area of the circle we're looking for, which is 99%, which is 15.84 pi. So we're trying to work out when we're going to get to that point. So it's another equation solving question. So we're going to make an equation, 15.84 pi. When is the sum formula going to equal that? Well, we'll stick the sum formula in. So 8 pi times 1 minus 0.5. And the thing we don't know, of course, is the power of x. So this x is the unknown here. And then that is going to be 1 minus 0.5. If you type that in onto the GDC, you will get the answer. But let's just do that one because it's a bit less obvious. So again, on the equation solver, let's type that in. So 15.84 times pi, and that's going to equal, get the fraction, 8 times pi times bracket, and then we've got 1 minus 0.5 to the power of x. That's the bit we don't know. That's going to be the x, all over 1 minus 0.5. Okay, and if we press the solve button there, okay, 6.64. So it looks like, well, we're not going to have to go very far. The 7th person is going to be shading in 99%. The 6th person wouldn't quite do it, wouldn't have quite 99% there, but the 7th person, they'll get that. So the answer is 7. Last question here, and this is the one that I previewed a moment ago with the interesting mathematical paradox. If the process was continued indefinitely, write down the area of the circle that would eventually be shaded. Now, this is a question that troubled mathematicians for centuries before, around the 18th century, it was finally answered. So this is not a trivial question at all. It's asking, if you carry on shading half and a half and a half and a half, are you ever going to completely finish shading the circle in? Well, it's an interesting question. Before we answer it, I'd like to show you a similar question that was posed a very long time ago, thousands of years ago, by a philosopher mathematician called Zeno. So you may have heard of this. It's called Zeno's paradox. And if you Google this, and I'll put a link in the description to a video of somebody talking about this specifically, maybe you'll see how it links to what we're doing. So just very briefly, the paradox is that Achilles, who's the fastest man in the world in ancient Greece, he was going to have a race on foot against a tortoise. So we'll call this little black thing here the tortoise, and then the other one down here, this is going to be Achilles. And obviously, Achilles is going to beat a tortoise in a running race. No question about that. But Zeno said there is a way we can say that Achilles would not win if we frame the question like this. What if the tortoise had a head start? So let's say it gets to about there. And let's put some numbers on this. Let's say the tortoise has a head start of 1 meter. They didn't have meters in ancient Greece, but we'll just use numbers that are convenient for us. And let's say Achilles runs at 1 meter per second. So every second he goes a meter. And the tortoise wouldn't be this quick, but it will make the maths a bit easier for us to work with. If we say that the tortoise runs at 0.5 meters per second, so he's running at half the pace. Okay, clearly though, you'd think Achilles would still win this race. But what if we model it like this? After 1 second, Achilles will reach this position, level with where the tortoise was at the beginning, but in that 1 second, the tortoise will have moved half a meter. So 1 second has passed, and they are definitely closer together, but not quite level. Okay, let's move forward in time a bit more. In half a second, Achilles will reach that position, because in half a second he can run half a meter. But in that half second, the tortoise can move 1/4 of a meter. Maybe you can see where this is going. In 1/4 of a second, Achilles catches up, but in 1/4 of a second, the tortoise moves 1/8 of a meter. And we'll do it one more time. In 1/8 of a second, Achilles gets to the same position. He's caught the tortoise up, but in that time, of course, the tortoise moves forward a little bit more. He moves forward 1/16 of a meter. Framing it this way, Zeno said that Achilles would never catch the tortoise, because although he's getting closer and closer and closer in shorter and shorter amounts of time, there's an infinite number of these little gaps. Yes, you can keep halving it, but you're never going to get to zero. There's always going to be a little bit more. And if there's an infinite number of these little gaps, even if they're really, really small, you're not going to be able to ever actually cross them, because there's an infinite number of them. And as a genuine paradox, nobody had the mathematical answer. Obviously, Achilles would win the race. Of course he would. But how do you answer this question? How do you answer the fact that there's an infinite number of these little gaps? How can he ever actually catch the tortoise if you think of it this way? And it's the same question here, really, isn't it? Are you ever going to completely fill this circle? If you just keep shading in a smaller and smaller and smaller, half the size, half the size, half the size, every single time, is it ever actually going to be completely filled up? The answer is yes, which is good to know, because it makes things a lot easier. The answer is yes for one kind of pleasing reason, which is that if we go to our nth term formula, which we had a moment ago for this particular question, which is here, this is the formula for the amount of the circle shaded in. If you look at this, if you increase this number n to infinity, it gets bigger and bigger and bigger, what actually happens there? Well, you get 8 pi times 1 minus, well, 0.5 times itself an infinite number of times. It's going to get closer and closer and closer and closer to nothing. Eventually, you're going to be multiplying such a small number that it's virtually zero. So that really is just times 1, and it's over 1 minus 0.5, which turns out to be 16 pi. That's just 8 pi, that's 0.5 on the top. 8 divided by 0.5 is 16, and 16 is the whole circle. And that's using the infinite sum formula there. You'll notice it's simplified down to the starting term over 1 minus r. So in our case, it's 8 pi over 1 minus 0.5, which is what we've got there. So that justifies it. Now, you might still be a little bit unconvinced that this would actually be true philosophically. The maths required to prove that this really would get to the actual answer is a bit beyond what we're doing right now. But think of it this way. If you're adding a smaller and a smaller and a smaller amount each time, eventually you're effectively adding nothing. And at that point, you will have actually reached effectively the full amount. And Achilles effectively will have caught up with the tortoise. Okay, hopefully that does answer some of those questions. Again, let me know if there's anything you're not quite sure about on any of the exercises.